Hello, everybody. So, welcome to the second AVSthon workshop that is hosted by Outlayer. Today, we have the really awesome team from Automata that's going to present to you about TEE. And the presenter today is Ona Babu. So, I'll add her on stage now. Do you want to say hi to everybody?
Hi, I'm Juana. I'm a DevRel at Automata, and my presentation today, I'm going to give you a brief introduction to these and also show you how you can easily use one of our libraries to implement your first TE application. So with that,
Uh,
yeah, should
yeah,
I
uh,
start or?
Yeah, definitely you can start. But before that, do you want to just shortly, briefly introduce to the audience what the Automata does, and also your role there as well?
Yeah, so I'm a DevRel slash researcher, and at Automata we are building this machine layer to attest devices, and we also have extensive experience with in working with TEs. We've been doing that for um, many years now. Yeah, and
I see.
we are offering a bounty on at the AVSthon for if you guys are going to build using our libraries, T applications, or if you want to use our attestation library, as I will mention about that later as well.
Yeah, thanks a lot, Luna. So, just to give you guys a quick review, is that we do have a bounty that's being issued by the Automata team, which is almost 5,000 USD dollars worth of ATA tokens that's given to the winner, who will be decided by the Automata team itself. And this is on top of the prizes that you can, of course, win from the main prize pool. So, if you guys want to tackle the TE problem, please listen in to her workshop right now, and you can also ask the questions on the Telegram chat group. So yeah, without further ado, Ona, please take the stage. I'll take myself off. Thank you so much.
Thank you. Yeah, so as I mentioned before, the presentation today is about one of our SDKs and building T applications. So in case you're wondering what the T is, it stands for Trusted Execution Environment and is a hardware enclave that's protected by the CPU. What this means exactly is that the CPU will encrypt the memory of the enclave such that only the enclave is able to decrypt it. That means neither the operating system or the hypervisor or any super user can access what's inside uh, the enclave. This provides code and data integrity and private execution. And in addition, a feature of a TE is this thing called remote attestation that enables a TE to prove that it's indeed legitimate hardware. We will touch upon this later. So there are multiple vendor implementations coming from Intel, AMD, even AWS has a TE, but today we are going to focus on Intel SGX. SGX stands for Software Guard Extensions, and it relies on Intel CPU to enforce security. SGX is what is known as a process-based TE, meaning that the process represents the TE. This is opposed to VM-based TEs, where the whole VM is your TE. And because SGX is a process-based TE, it has a minimal TCB, trusted computing base, which basically is represented by the code that you want to execute in the enclave and the CPU. Whereas when you have a VM-based TE, your TCB is the whole VM. That means your operating systems, other applications that you run on top of it. So the TCB is much larger. And in general, we prefer a smaller TCB because it leaves a smaller area for attacks. And interaction with the TE is protected, so there's there is a secure communication between the enclave and the outside world. And so Intel SGX application is represented by two parts. On one side, we have the untrusted part of the app, and then we have the trusted part. And the untrusted part is responsible for creating the enclave, calling the appropriate interfaces in the enclave, and if the enclave, the trusted part wants to make any outside calls, it will do this via the untrusted part. And as I mentioned before, there's no entity that can access anything that happens inside the trusted part of the application. And the interaction between the trusted part and the untrusted part is done via these things called e-calls and out-calls. So an e-call is an enclave call. It's a call made from inside the enclave. So for example, here, when we call the trusted function inside the trusted part of the application, we are basically making an e-call. And if the enclave wants to call this function A, which resides in the untrusted part of the application, then it will make an O call. So we developed this SGX SDK. It's open source. You can access it at the link shown on the screen. And this SDK provides a general development guide for building secure enclaves in Rust. And on top of it, we build this SGX scaffold library that is a template that will enable you to easily create enclave based on the Automata SGX SDK. And basically, I want to show you today roughly how that works, how SGX scaffold works. So if you go to the repo, you will find here a brief introduction about the application and the code that you can modify to implement your own application. So I have here the repos. So the repo contains the application, which has the SGX part, and in the SGX part you will find this config file that basically contains the defined parameters of your enclave. You will probably not have to modify this file. Here you can specify, for example, the maximum stack size or the heap size and so on. So unless you need more hardware resources, you will not have to touch this file. Then we have the EDL. EDL stands for Enclave Definition Language, and this is basically where you define your e-calls and o-calls, like the functions that you want to use to get inside the enclave and outside the enclave. And here, for this template, we've defined an e-call that's called trusted execution, and an o-call that's called untrusted execution. And we also import here the frequently used EDLs that you'll probably need to implement applications. Then we have this LDS file. This is just a linker script. You don't have to worry about it. And a private key, which is the developer key that is used to sign the enclave. So you will want to modify this. There's a command for using that in the repo. And then we have the main application. This is the starting point of your application. As you can see here, we defined the the enclave with its eCall, the trusted execution eCall that we saw defined in the EDL, and the main function is basically what will be executed when we start running this application. And in this case, we create an enclave. This is what I'm not sure actually if people are familiar with Rust. But in case you aren't, so here we are creating this enclave object. Then we call the trusted execution method on it. And then we are unwrap because this trusted execution uh, will return what's called the result in Rust, which can be success or error. And here we just assume that it's successful and we unwrap it. And this result has the type SGX status, which can be success, unexpected, and some other value. So in case the result is not success, then we want to print out the result and see what happened there. Okay, and besides this, we have the cargo toml for the app, in which we specify the dependencies that we want. So we depend on Automata SGX SDK. And the mocklib is the library that contains our untrusted definition, like this call here, the untrusted execution method. So we have to import that. And here we also specify some things about our enclave. So we specify where the enclave code is located. We will go here in a minute, and then also the config, the EDL, the LDS, and the key files. Okay, so then we have the enclave code. So the enclave code is what gets executed inside the SGX, and you should probably guess by now, but that here is where we basically define our eCalls. In this case, we only have one eCall, the trusted execution method. So this is where we defined it. This function does some very basic things. It creates here we create a JSON object, and we print it. Then we also pretend to create a random number, and we use this random number to call the untrusted execution call, which, by the way, we have to declare it here, such that the linker knows that we have this method defined somewhere. And after we do the call, we come back to the trusted execution, and here we will just generate an attestation report and print it on the screen. And the enclave also has its cargo toml file where we specify the dependencies. So here we depend on SERDI, for example, for the serialization. And lastly, we have the mocklib that just defines this untrusted execution method that takes in an integer, and we just print it on the screen. Okay, so we can actually compile this. We have this cargo SGX utility that you can use to build and run code easily. So I've already built it before, so it won't take too long. And then we can use the cargo SGX run to execute it. So if we are to look here, so this is when we start the application. This is printed from the app folder. Then we go into the trusted execution part, where, if you remember, we serialized an object. We also generating a random number, which was 4, and then we use this number to make a call to the untrusted world. So this is printed from the mock library, And then once we got back to the trusted world, we generated the decap attestation. And that's the end of the application. So if, let's say, we wanted to add another eCall, so first thing that we would have to do is create create the eCall. So let's say we call this additional function, we call it demo, and you could this is basically where your T code goes into. I mean, of course, you can also modify the trusted execution method to do some other sorts of logic that you wanted to do. But if, let's say, you want to have multiple equals, then I'm just going to show how what are the steps that you have to do in order to define another equal. So here we write the implementation of the equal. Let's say we just print, this is where your the application does its work. And then we can just, we have to return the status, the SGX status, and let's say, of course, it's successful. So now we implemented the eCall. We also need to, of course, define it in the EDL file. So here we will have another function. This function returns the SGX status, and is called demo. And in the main application, we also have to specify that our enclave now has another, an additional eCall that returns SGX status, and here we can actually call it. So let's say we or so if we want to reuse the same enclave, so we just define the enclave separately. Then we use the enclave to call the trusted function, and then we also use the enclave to call our demo function. Okay, so basically like this, we created another okay, I have a typo here. Okay, yeah, so we just defined another eCall for our application. Okay, so now I'm gonna go and go back to my slide. So again, these are the links. This is the SGX SDK, and this is the template, the SGX scaffold that we just used. Okay, and besides the SGX SDK, we also implemented a library, the decap library for verifying attestations. So why is it important to verify attestation? So let's say we have two chips. One of the chip is a legitimate SGX chip, and the other one is fake. So how how do I know that one of them is fake and the other one is actually genuine? This is where remote attestation comes into the picture. So unless so remote attestation is the process via which a remote party requests an attestation report from an enclave. And unless the enclave is actually a legitimate, it runs legitimate hardware, it cannot produce a valid attestation report. So in this case, because the enclave on the chip on the left is legitimate, it was able to produce a valid attestation, whereas the one on the right isn't. And the attestation report that it tried to fake, we will be able to identify that that the report is fake. And basically, what the remote attestation report contains is the enclave identity, which is a public key, a set of measurements of the enclave, for example, the firmware, the software that's run on the enclave, and also, and this information will be signed using the private key that corresponds to the enclave identity. And this private key is only known by the enclave. And the reason why we know that private key corresponds to an actual Intel SGX hardware is because Intel itself will recognize this private key, or rather it will recognize the private key that corresponds to the to this private key. So basically there is a X509 certificate chain that links Intel to the public key that's associated on the with the TE. And actually, when we verify an attestation report, we verify that all these the certificates are legitimate and up to date, and so the chip is legitimate. And we basically implemented a library that allows us to verify this attestation on chain. So the attestation is done via this thing called DCAP, which stands for Data Center Attestation Primitives, and is the set of APIs that handle attestation verification. And we implemented two versions of it. So there's DCAP v3 and v4. We can verify both on chain using the DCAP library. This library works not only for Intel SGX hardware, but also works for TDX, which is TDX is Intel's VM-based TE. And so the problem with verifying DCAP attestation on chain is that it's a bit expensive. Like I mentioned before, during the verification process, we verify an X509 certificate chain, and this certificate chain uses P256, which is not supported directly by Ethereum, by the EVM. And because of that, it can be a bit expensive. More exactly, an attestation report costs about 4 million gas to verify. And in order to make to reduce the cost, we also have an alternative to verify a NARC proof, a zero knowledge proof, instead of verifying the attestation. So basically what we do is that we run this risk zero program that produces a snark that proves the attestation is correct. And instead of verifying the attestation, now we just verify this snark proof, and it's actually cheaper to do that because it only costs like roughly 300 K-gas to do this on chain. And we've deployed the contracts that do the, that do this both on Automata and Ethereum. So let me show you roughly. So this is the decab library. Some basic, sorry, it's not this one. It's this one. Yeah, so some basic information about the course, what I mentioned before, also like how you, if you want to run it locally, how to do so with Foundry. And here we have the addresses where the contracts for verifying attestations are deployed. So if let's say we go to Automata testnet, we can actually, you can go through the contract, but what I want to show you is how we can use the contract to verify the attestation. So if you remember, when we ran the code, we actually generated an attestation report. So we can just copy it and we can use this to verify on chain. And I am running this on a genuine Intel SGX hardware, so the attestation verification was performed successfully. And actually, let me show you one more thing. So when we ask the hardware to produce an decap quote, quote is Intel's way of saying attestation. We specify some data. So in this case, this data is just a bunch of zeros, but this is a field that we can use to attest on some data particular to our application. So let's say I generate a private key inside the enclave, and I want to show that this private key, or rather the public key part of the key, was generated inside the enclave, and I want to say, hey, you can trust this public key. Only the enclave knows its private counterpart. So we can actually use this data field to attest on this public key, or whatever. Like if you want to provide an attestation that today is 21st October, then maybe you use the string 21st October as the data field, or like any data that's important for your T application, and you want to prove that this data is indeed generated inside the T, then you can use this data field to do that. Okay, and actually that concludes my my presentation. I hope you guys use our tools to develop cool things. You can find more about us on X, or you can read our docs, join our Discord, and if you have any questions, feel free to reach out in the Telegram chat. Once again, our requirements for the bounty is that you use either the decap attestation or the SGX SDK library, or both, of course. And yeah, that's it from me.
Yeah, thank you very much, Ona, for the wonderful presentation on TE. I hope you guys have a good, better insight into what the TE actually does in the blockchain space, and what we can actually do as well for the AVS hackathon. So without further ado, we'll close the session. Thank you for your attention, and we'll see you next time. Thank you very much.
Bye.
Thank you.